Hello, everybody. I hope you can hear me well. Yes, great. So we are beginning this third webinar of the series around the coronavirus. Today we have Professor Shai Arkin of the Structural Biochemistry and former Vice President of Research and Development Unit at the Hebrew University. He will speak about the coronavirus and the future of immunotherapy, and he will shed some light on this emergency situation that we are all living around the globe. So please, Professor Arkin, the floor is yours.
Okay, thank you very much, Mara. So without any further ado, let me start. So I'm assuming that you hear me. One or two points. The first thing that I'd like to do is to welcome you all to this webinar. And in fact, since this is in my house, I should say that I'm welcoming you to my house. And one second. Apologies for this. Okay. So I guess we're starting. So let's see what's on the agenda for today. The first thing that I'd like to do is to provide you with a disclaimer. And if I'm looking from time to time on my telephone, it's because I'm looking for help from the IT group. So as I said, what are we going to do today? The first thing that I'm going to do is to provide you with some sort of disclaimer. And because I'm assuming that what everyone is looking for is information on what's going to take place in the future, and that's going to be something that I'm going to be very vague about, not because I wish to be, simply because it's very difficult to predict what's going to take place. So what I thought of doing is actually to provide you with a solid foundation that you yourself should be able to evaluate critically all the information that you are currently inundated with. So we're going to start with thinking about what are viruses in general, because we hear more about them today probably than we have heard in a lifetime. I'd like to tell you a bit about what are the differences between virus and bacteria. More importantly, how can we combat viruses? And why is this such a challenge because of viral resistance, etc. And then we're going to move on to coronaviruses, which is obviously the reason why we are all gathered here. What are they? Where did they come from? And obviously, you know, this disease that we are all only too familiar with today, COVID-19, what are the challenges? What are the prospects, etc. And then we're going to have plenty of time for questions and answers. I'm not sure how good the answers would be, but I'm certain the questions will be. And one thing that I'd like to do is, as it said over here, please raise your hand digitally for questions, okay? Let's not try to use the chat, because that will allow me to administer this a bit better. Okay, so disclaimer, what am I not? First and foremost, I'm not a physician. And that's important for me to say. Nothing that I'm going to say today will result hopefully in something that you will immediately think, you know, a doctor told me to do this, and therefore that's how I should act. I'm not a doctor, nor am I an epidemiologist. I'm not necessarily certain that epidemiologists today are capable of predicting what will take place, but they are the people that are responsible for this realm of science. And in fact, I'm not necessarily certain that I'm a true virologist in the sense of the word. So you're asking me, what am I actually? Okay, they're telling me to put more light on. Let's see if I'll try to do that. I'm in the dark. Is this too much light? No, this looks like I'm in the sort of investigation. How about this? Is that better? Okay, let's try that. So what am I? I'm a biochemist, and I study the inner workings of viruses. And the two subjects that I study most are influenza and SARS. So I do understand how the SARS virus works. And because of that, and what I'll tell you about in the very near future, obviously, I am somewhat of a maven in these topics. Okay, So let's start from the very beginning, because once again, we need to be able to evaluate all the information that is streamed at us at amazing paces today. And what are viruses? And I'll like to try to do this in plain English. So let's start from the very, very obvious. Viruses are tiny, okay? But there are lots of things that are tiny. A grain of rice is tiny, a grain of sand is tiny, bacteria are tiny, our cells are tiny. You know, how tiny is a virus? So here's a scale that you can actually evaluate. So you can see the flu virus, which is the fourth item from the left. And a flu virus is about 1/10 of a millionth of us in terms of length. So it's much smaller than a bacterium. It is much smaller than one of our cells. And obviously it is much, much smaller than we are. So again, you need to put about 10 million viruses in a row, and then they would result in something that is of our dimension. But in terms of volume, obviously that then is exacerbated dramatically. And if you want to think about a volume, but before that, let me just say one or two things about how we can actually look at viruses, excuse me. The stuff that's currently shaded is the information that we are able to discern with our naked eye. So we can only see human eggs, but we can't see any cell, and obviously we can't see bacteria, nor can we see viruses. If you have a light microscope, a regular microscope, you might be able to see the largest viruses out there in the world, but not the coronavirus. In order to see them, what you would need is you would need an electron microscope. So these things are very tiny. But what I thought I'd do is to provide you with a better feel. And one is by way of ratio. So let's think about the volume. So how many people can one fit inside the sun? The sun is probably the largest object that most of us are familiar with. So we can fill a huge number of people inside the volume of the sun. That ratio is very similar to the ratio of us and a virus. So viruses are really, really small. Each one of the cells in our body can contain 1 billion viruses. Now, if we're thinking about the fact that viruses are so tiny, we immediately need to think about how effectively can a mask prevent viral infectivity, okay? And we might talk about that later on. So viruses are tiny, but the reason that we're concerned about them is not because of their size. The reason that we're concerned with viruses is obviously because they are genetic parasites. They're genetic parasites that act as infectious agents. And how do they do this? Well, they do this by commandeering our resources, okay? They actually insert themselves inside our cells and replicate and make new viruses as if we are an industrial site for their production. And they do this in a multi-stage process. First of all, they need to absorb to our cells, then they penetrate, and then they replicate. The virus is then matured and then is released. And you see many, many such viruses can be released from a single cell. It can be tens of thousands, if not more. So these are infectious genetic parasites that overtake our own cellular machinery in order to make many, many more of them. Now, one thing that we need to appreciate that viruses are amazingly diverse. And the reason that I'm stressing this is because you might think, well, you know, we know how to deal with HIV, the causative agent of AIDS. We know how to deal, for example, with hepatitis C. Why can't we deal with this virus? Why is it so different? After all, an antibiotic against one bacteria is very often effective against another. What's the problem? Well, viruses are amazingly diverse. Let me just show you that viruses can in fact infect a huge number of organisms. Nearly every living thing on the face of the planet can be infected by a virus. So on the left, obviously you see humans in several different representations. Viruses infect us. On the bottom right, you see bacteria being infected with special viruses. Viruses that infect bacteria are called bacteriophages. And on the top right, you see plants. And this particular plant is tobacco, and the virus that infects that is called tobacco mosaic virus because it forms these sort of mosaics. So viruses can infect nearly every creature on God's earth. Now, not only that, if you actually look at them, you immediately realize that they're dramatically different from one another. And here are some famous viruses. You know, on the top right, we have the Ebola virus that looks something like a snake. To the bottom of the Ebola virus, we have bacteriophage. Infects bacteria. It looks like something on an alien movie. To the top left, we have HIV, the causative agent of AIDS. And you see that these things are dramatically different. And in fact, it's safe to say that viruses are more different from one another than we are different from bacteria. Let me repeat that. The difference between us and bacteria is smaller than the difference between different viruses. And that's why there is no one solution hits all, because they are so different from one another. And just to put this in scale, because the previous picture placed all the viruses in the same sort of size, on the left, you see hepatitis B virus, and on the right, you see Ebola virus, and you realize that one of them is about 100 times bigger than the other, okay? So they vary dramatically from one another, and that's why we need to combat each and every one of them differently. Another question that people often ask, are viruses alive? I mean, are there living creatures? You might also hear very often people say, what is the life cycle of a virus? Well, if something isn't alive, does it actually have a life cycle? So let's have a look at this. These are criteria that most people use in order to evaluate if something is alive or not. Do viruses grow? Viruses do not grow. They never change in size. Do viruses reproduce? Yes, they reproduce. They reproduce in a different way than we do. We reproduce by taking one cell and dividing it into two. Viruses are assembled like an assembly line. Metabolism. We metabolize, obviously. All living creatures are thought to metabolize. We ingest food and we secrete waste products. Viruses don't eat. They don't metabolize. They utilize our resources. Homeostasis. What does that mean? Homeostasis means that you can control your internal environments regardless of what takes place outside. Viruses are incapable of doing that because, once again, they have no utilization of energy. The concept of metabolism does not exist in viruses. Response to stimuli, it's not really clear if we can define viruses as responding to stimuli. So once again, that's probably an if. Internal organizations, yes, viruses have a very intricate internal organization, and viruses clearly evolve. So if you want to answer the previous questions, are viruses alive? You are probably left with an ambiguous question, but at the end of the day, does it actually help us to combat them? The realization if viruses are alive or not, I think, is not necessarily correct. Another thing that people are often confused, what is the difference between viruses and bacteria? This is another major question that people have. Let me try to answer that. So first of all, characteristics. Bacteria are living organisms. Bacteria do test positively on all the criteria that we previously mentioned. They divide, they replicate, they metabolize, they do all of the things that we do as living organisms. Viruses, on the other hand, are genetic entities. Both bacteria and viruses are responsible for dreadful, dreadful diseases. And I've listed just a list of quite frightening diseases that bacteria are known to elicit. The plague probably be the most famous, that decimated a third of Europe. The bacteria that caused that is called Yersinia pestis. Tuberculosis, cholera, anthrax, Lyme disease, syphilis, gonorrhea, urinary tract infections, meningitis, pneumonia, and even the strep throat that we go to the doctor every so often to receive antibiotics for. So those are some of the diseases that bacteria cause. Viruses also are known to cause dreadful diseases. Influenza, the common cold, hepatitis, both B and C, AIDS, smallpox, which is one of the most dreadful diseases in the history of mankind, rabies, Cancer, believe it or not, it's thought that 20% of cancers today are caused because of viruses. Perhaps the best known is the one that ladies receive vaccination for, papillomavirus. And of course, COVID-19, which is the disease that we will talk about in a few seconds. How does one treat bacterial infections and bacterial diseases? Well, one can utilize vaccination in exactly the same way that one utilizes that for viruses, and antibiotics. And if there's something that we always know of, is that if it's a viral disease, well, you shouldn't use antibiotics. Well, there are actually small chemicals that can be used as antiviral drugs, and I'll talk about that for a second. What are the challenges that bacteria and viruses pose to us? And I've decided to divide this into developed countries and developing countries. So to developed countries, believe it or not, bacteria don't pose that much of an issue. There are other things that frighten us much more. If you look at the CDC in the United States and you ask yourself what are the 10 leading causes of death, you're not going to find bacteria there. Okay? And the biggest issue is antibiotic resistance, these strains that are no longer susceptible to any sort of antibiotic treatment. Viruses. So viruses do pose somewhat of a challenge to developed countries. Influenza is the leading cause of death amongst infectious agent, but still it's less than 10% of the mortality that's inflicted by things like cancer and coronary disease, etc. And obviously today, we can't overestimate enough the impact that COVID-19 has on the life of people all over the world. And yet the challenges to developing countries by bacteria and viruses are huge, okay? Dysentery, pneumonia, diarrhea, tuberculosis exact a huge toll on developing countries all over the world, with millions upon millions of people dying due to bacterial infections. AIDS is probably the most important virus in Africa today, exacting again hundreds of thousands, if not more, deaths annually because of that, and there are more viruses there. Okay, so how do we combat viruses? And after that, obviously, we'll talk about how this helps us to combat the virus that causes COVID-19. So there are three general routes that you're all familiar with. Vaccinations. What we do there is try to elicit an immune response by your body. And we do that with an agent that does not elicit the disease. So you can either take an attenuated virus, a dead virus. Again, I'm using the term dead, even though I'm not certain that a virus is alive. We can take parts of the virus, fragments of the virus, and inject that into people and hope that they develop antibodies against those fragments. And again, we're all familiar with this. We get our flu shots every season. We have smallpox vaccines. This is an incredibly effective way to deal with viral threats. Drug therapy. You probably have heard about the cocktail that can pretty much cure AIDS today. So it's incredibly effective against HIV. That's probably the best example. We can deal with hepatitis C virus quite effectively with novel drugs, small compounds that we can ingest. There's also some drugs against influenza, if it's Tamiflu, etc. So that's another option. The third option on the bottom right is someone is slightly less common. So what you're doing here is you're actually using antibodies that someone else made for you. Okay, so what you're doing here is you're actually ingesting somebody's serum after that individual developed immune response to the viral problem that you're facing. We're most familiar with this with anti-snake venom, etc., but this can also be used for viruses. In the SARS epidemic in 2003, this was actually used. A serum was taken from people that recovered from the disease and was given to those that didn't, that were currently suffering from the disease. Okay, but what about viral resistance? Why is it that we take a flu shot every year, but we only take a smallpox vaccination once in our life? Why are we concerned about viral resistance? Well, so Viruses, like ourselves, replicate their genomic information, and they do that not nearly as effectively as we do. So what you see on the right is our genetic information. That's the famous DNA, deoxyribonucleic acid. And each one of those lines is a letter in the code. And when we replicate our genetic information, we do this amazingly well. We only have one mistake every 100 million letters that we replicate. Viruses do that about 1 million times worse. And that's why viruses continuously change. They change 1 million times faster than we do. So the antigens of today, the virus of today is not going to be the virus of tomorrow. And that's why we might need flu shots every year, okay, in order to follow this rapidly evolving virus. So finally, we get to the subject at hand, coronaviruses. So what are coronaviruses? So here you see a picture on the right. Coronaviruses are RNA viruses. What is an RNA virus? It simply means that the genomic information of this virus is stored as RNA. Doesn't really matter. It has these strange protrusions on its exterior, and that's where the name comes from, corona, a crown in Latin, and that's why it's called coronaviruses. Coronaviruses are known to infect mammals and birds, and if you were a farmer, you have probably already heard about coronaviruses because in livestock and poultry, coronaviruses exact a huge and high morbidity. So one of the more famous epidemics that are caused by coronaviruses are porcine epidemic diarrhea virus. In cattle, also transmissible gastroenteritis virus. Some of these viruses, by the way, do have a vaccination, okay? These livestock and poultry coronaviruses. In humans, coronaviruses cause respiratory tract infections that are mostly mild. In fact, I would probably venture a bet that most of you have already incurred a coronavirus disease, but normally it's very mild. In fact, you are familiar with it as the common cold. It's not the major agent of the common cold. Rhinoviruses are somewhat more prevalent, but again, most of you have already been susceptible to viral infections from coronaviruses. Once again, we're not talking about the common cold today, and that's where the big however comes into play. However, every so often, a rogue coronavirus makes an entry, makes a debut. And 3 of them in the last 2 decades have really set a significant toll. In the winter of 2002-2003, there was a disease called SARS, which stands for Severe Acute Respiratory Syndrome. The virus was therefore named SARS coronavirus 1. There were about 8,000 cases and about 770 deaths, and that leads us to a mortality rate close to 10%. So 1 out of 10 people that had SARS died. In 2002, and it's still dwindling, but to very small numbers, another coronavirus made an appearance. This time it's called Middle Eastern Respiratory Syndrome, and that's where the virus is called MERS coronavirus. It only had 2,500 cases and about 860 deaths, which means that this virus was incredibly virulent, with close to 1/3 of all the people that incurred the virus have died. And today we're familiar, obviously, with COVID-19. It's called COVID-19 because it started in the winter of 2019. It's called COVID because it's from a coronavirus disease. The virus name is actually called SARS coronavirus 2, and I'll say a few words about that. And as of March 18th in the morning, the number had probably increased. There had been around 200,000 reported cases with about 8,000 deaths, which results in a mortality of 4%. So where did they come from? This is probably the most important question that many of us are asking. What is it that resulted in the emergence of these 3 very virulent coronaviruses? So what they probably have done is they have crossed the species barrier. So viruses often have a natural reservoir that is very hard to identify. This is an animal very often a mammal, but sometimes it can also be a bird, that the virus simply lives there. It might exact a toll from that host, it might not, etc. And the virus can then be transmitted to humans through an intermediary host, so not necessarily directly. And diseases that are transmitted to us by animals are called zoonotic diseases. And therefore, and this is one thing that I can qualifyingly say, consumption of wildlife animals increases the risk dramatically, because what you're doing is you're sampling more and more animals. It's always a good idea to know what you eat. So specifically, let's talk about SARS 2002, 2003, 18 years ago. The original reservoir is thought to be the Chinese horseshoe bat. And what the bat does, as what most bats do, is when they eat fruit, they take a bite, they suck up all the nutritional sugar, and then they throw the fruit fiber on the floor. Well, on the floor, you might find an animal that's called a Himalayan palm civet, and the civet eats that fruit. And then, for reasons that are somewhat unclear to me, people decide to eat the palm civet, and then they get the disease. Okay, so either you eat the bats directly, or you eat an intermediary. To make a long story short, you get it at the end of the day from the bat directly or indirectly. So that's SARS in 2002. MERS, Middle Eastern Respiratory Syndrome, also is thought to have originated from a bat, in this instance, the Egyptian tomb bat. And in this instance, it was delivered to us via the dromedary camel, which people in the Arabian Peninsula are known to eat. And again, because they did that, they incurred MERS, which killed 1/3 of all the people that incurred the disease. And today, COVID-19, we assume that it came from bats because it's very, very similar to viruses that were found in bats. I say very, very similar, but not identical. So we don't know for certainty, but it's probably a very, very, very good assumption. It's thought not to have come directly to us from bats, but rather via another animal that once again ate something that bats threw away, the pangolin. But again, here we are not absolutely certain. So again, another very good suggestion on my part will be don't eat bats, don't eat camels, or don't eat pangolins. And if you do, make sure to cook them properly. So what about COVID-19, this disease? This is the name of the disease. And this is probably what you are familiar with. This is a website provided to us by Johns Hopkins University that tells us the overall cases per country all over the world. And you can see that every day these bubbles become bigger and bigger. And it's very difficult to find a spot on the planet where cases have not been found. Okay? And you can see that the total confirmed cases are about 200 and some odd thousand, and the total deaths are about 800,000, with the countries that are leading are obviously China and Italy following rapidly after that. Okay, one thing that's very important to realize is that this disease is tremendously effective and lethal to elderly. And what you see over here is the fatality by age group. And this mirrors...
Sorry, I couldn't hear what you said.
Excuse me, someone's trying to reach me. Ah, okay. This disease mirrors, to an extent, influenza, which influenza for the majority of the population who are not classified as elderly is only a problem that sets you back about a few days from work, but for the elderly, it really is life-threatening. This is also mirrored in COVID-19. You can see those of us that are 80 years or older, the fatality is 18%, 70 to 80 is close to 10%, and if you're below 50 years old, the chances that you will die from this disease are much, much, much smaller. Another thing that is interesting is that the fatality by gender is not equal. Men are about twice as susceptible to meet the Almighty because of this disease than women. And one of the thoughts for this discrepancy is that the receptor for the virus, that's the bit on the cell that the virus can attach itself to, is actually coded on our X chromosome. Women have 2 copies of the X chromosome, men only have 1. Now, we're not certain if that's the case, but it is curious to show that the fatality by gender is very, very different from men and women. Okay, so what are the current efforts to try to cure this disease? And obviously, number 1 is vaccine. And it's safe to say that the vaccine development for COVID-19 is progressing more rapidly. There's at least a dozen trials underway all over the world, and this is faster than anything that we have ever seen. And what I'm going to do right now is give you 2 statements that will probably make any politician proud, because I'm going to be very vague. So it's unrealistic to say that we will have a vaccine within a few months, but it's probably not entirely unrealistic to say that we will have this within a year. So there are no assurances. Again, a few months is unrealistically fast. A year, I would say, is a very good achievement, and we might be able to reach that, but that would be a really a tremendous success story. So bad news, a bit of pessimism. There are some viruses out there that we have never been able to get vaccines against. I repeat, some viruses that are very important biomedically, such as HIV or hepatitis C virus, despite our very best efforts, we have never been able to get a vaccine against. Having said that, there's no reason to assume that we will not be able to get a vaccine against this coronavirus, because we were able to get vaccines against coronaviruses that infect animals. So there's no reason to assume. A bit of good news. As opposed to the flu that changes so rapidly that every year you need a new vaccine, this virus does not seem to be changing as fast, so vaccination will probably be effective the moment that we come up with it. Okay, so that's that for vaccination. Stay tuned. Current efforts to cure, what about drug development? So are we going to be able to develop a Tamiflu against COVID-19? So to develop a new drug on the market takes a long time. Normally, you're talking about years, because regardless of the development process, you have clinical trials, phase 1, 2, and 3. So here I would say best case scenario is probably a few years. Obviously, the regulatory loops might be broader, and the FDA and other such agencies might be more willing to enable us to go through these hoops faster, but this is going to take some time. Having said that, there's another option which has become quite common, and that's drug repurposing or repositioning. What does that mean? It means that you take a medication that was approved for use for one disease and use it against another disease. And there have been several very notable examples, perhaps the best of which is Viagra, which was initially developed against high blood pressure, angina, etc., and then was, of course, utilized for erectile dysfunction. The best thing about drug repurposing is that it's far faster, because all of the toxicology, all of the bad side effects have already been figured out. You see, it doesn't really matter if you're taking the drug against a liver problem, baldness, a high blood pressure, etc. It doesn't really matter. All you need to do, again, once you figured out the toxicology, the regulatory process is much, much faster. And there are already several candidates on the horizon that people are investigating. And I should also say that's what my group is doing. We are investigating current drugs that have been approved for use against other diseases to see how effective they are in curbing the SARS coronavirus 2, the agent that causes COVID-19. So 2 last slides, challenges and open questions. And here I'm setting questions that I don't necessarily have answers to. Actually, let me qualify that. I don't have any questions I don't have any answers to, and I'm not certain that anyone does have. One of the biggest challenges is to answer the following question: how many people are asymptomatic? And by that I mean, it could be that there's a huge number of people around the world that are actually carrying the virus, but are simply exhibiting no symptoms. So it could actually be that 50% of the population have already been infected by this disease, but have simply not realized that because they have no symptoms whatsoever. Are these actually people contagious? We don't know that, okay? Why don't we know this? Because we haven't been able to test people rapidly. We all know that one of the biggest concerns is that to test people as quickly as possible, and these tests are in short supply. So obviously we can't go ahead and start testing people that don't exhibit any symptoms. Another challenging question is, for how long are people contagious? Okay, are they contagious when they're asymptomatic? If they pass the disease, are they still contagious, etc.? Another question that we don't know at this point, but I think it's safe to say that it is probably true. Does recovery confer long-term immunity? The answer here is probably yes, because the virus has not seemed to be changing that rapidly. And perhaps a psychological question is, how long can the measures that we currently take, which are termed social distancing, sort of having people stay away from other people, how long can we sustain these measures? In totalitarian regimes, you know, these can be enforced quite effectively. In democracies, etc., perhaps less so. And obviously the question that we're all very concerned with, and I'm probably going to be asked, and I'm not going to be able to provide you an answer, so be forewarned, when will this end? I don't know. So my final slide is the prospects. And what you see over here, on the x-axis, on the bottom axis, you see dates. Okay, it's relatively small, but it starts from January 20th. I'm going to need to squint my eyes as well, and it ends up at March 17th. And on the y-axis, on the vertical axis, you see the number of cases. And in orange, you see what happened in China. In China, it plateaued in mid-February. There are virtually no more cases, no more new cases in China. So China beat this. What happens in the non-China part of the world? Well, there's no reason to assume that what happened in China will not take place elsewhere. Okay, so what we should concern ourselves is not the total number of cases that you see escalating day by day, but as the brilliant Nobel Prize winning American-Israeli scientist Michael Levitt says, what we should concern ourselves with the percentage change. So even if, for example, every day we have 100 cases in addition, the actual percentage dropped because we have far more people that are infected with the disease. And that's precisely what happened in China. So I think the underlying message that I'm trying to broadcast is, we're not going to hear about millions of people dying because of this disease. Remember, China is close to a quarter of the world's population, maybe a fifth of the world population, and it had about 2,000 deaths because of this disease. There is no reason to assume that the rest of the world would act dramatically different. Okay? So with that, I hope to have armed you with a bit of basic information about what viruses are, what we should be doing to combat viruses, what are this coronavirus that we're all afraid about and heard about. And what I'll try to do right now is negotiate myself through this mechanism and entertain questions. So let me see, how do I do this for a second? Oh, okay. So, wow, we have 184 participants. Okay, so what I'd like you to do is raise your hand if you have a question. And what I'll try to do is I'll answer this on a first come, first serve basis, okay? Okay, so the first question seems to be from My very, very good friend, proud to say, Monica Lobel. Okay, so I'm going to allow you to talk, Monica. Go ahead.
Can you hear me?
I hear you wonderfully well.
Okay, so I don't know if it would be possible for you or anyone else to predict the reoccurrence of this virus during next season by looking at the recurrences of SARS and MERS.
Okay, so I'm muting you. So reoccurrence. So MERS and SARS did not reappear. There was no free cases in the wild, if you will, of SARS in 18 years. Absolutely nothing. The only person that suffered from SARS was actually a graduate student in China that was working on the disease. So SARS, came into the world from nothing and disappeared into thin air. MERS, roughly the same. Will this thing come again? We don't know. The only thing that we can say is now that we've had a very large number of viruses sequenced, they're all very, very, very similar to one another. So at least we can imagine that those people that have suffered from the disease or were exposed to the disease, the antibodies that they have developed will probably be useful for them for next year. Okay, Julian, go ahead. Julian, can we hear you? Julian Dake? Let's see. Okay, let's, if you don't mind, let's get back to you after that. Okay.
Hello, can you hear me?
Yes,
great, thank you. I thought you were chatting. My question is, I saw what you did in the chat. When I see the distribution of the pandemic, I
don't hear you very well.
Okay. I see that there's a high correlation between infection rate, and a certain population of mortality. Is there a possible connection between the corona outbreaks and the coronavirus virus?
Julian, I'm going to have to mute you because I cannot hear you. Let's try to see. Perhaps you can write a chat and I'll answer after that. Okay, so I'm going to go next person, Vladi. How are you, Vladi? Okay, go ahead. Vladi? Oh. Vladi, can you speak?
Yeah, I can. Can you hear me?
I hear you wonderfully. Excellent. Go ahead.
Well, nice to meet you this time virtually, and thank you so much for the knowledge that you share with us. So, from your understanding of studying those viruses, you see this particular COVID-19 able to last much longer than the regular flu season that is usually 4 or 5 months. Can this last for an entire year, regardless of the weather that kills the other viruses, more or less?
Okay. Thanks, Vladi. Excellent question. I don't necessarily think that this virus has been lasting for a long period of time. In Israel, the first case that we had was only about 2-3 weeks ago. In the States, again, this was not a huge issue about a month ago. So in terms of a season, it hasn't increased normal flu season that starts anywhere from December and until March or April. So this is not something that is exceeding the time span. Do we know, though, when this disease will finish? We don't. SARS ended in end of May, beginning of June, and we're hopeful that that will take place over here as well. Okay, Moti Anavi, please. Okay.
Hello.
Hi, Moti.
Hi. Thank you very much for a great presentation. The question I had relates to testing. There seems to be taking a very, very long time to get testing going, and still it's in very, very small quantities. Can you explain why it's taking so long to develop actually a test and verification for this?
Okay. Okay, why is it taking so long to test? The standard procedures that we use in order to state, you know, is this or is this not this particular disease is not an immunological one. So you can't use the sort of test that one uses, for example, for pregnancy or even for a strep throat. And the reason is simple, we don't have antibodies against it yet. So the test that we are actually doing is we are searching for tiny amounts of their genetic information, their RNA inside our body. And that takes several hours. And the machinery that does the test is quite complicated. So again, this is going to take a long, it takes a long period of time, but I'm already hearing calls from the Ministry of Health in Israel, and I'm certain that in America it's taking place as well, asking for the help of universities that have all of these instrumentations there. So I would imagine that the time for testing is going to decrease dramatically in the relatively near future. Rebecca Gift.
Yes, hi.
Hi.
I'm very interested in knowing if people, especially doctors, who always or quite often claim that they don't get sick because they've come in contact with everything, if they will have a higher resistance or no resistance at all. And I understand that there's a very high death rate amongst doctors who are on the front lines facing this. Could you comment on that, please?
Okay, so I don't know about the death rate, but I can definitely say that there are clear, that there are, numerous doctors and nurses and medical staff that have incurred the disease. I don't know if the death rate is faster, but in Israel right now, this is a big issue because we have, half of a ward of a hospital shut down and people put in quarantine because they incurred the disease. So because this particular coronavirus is so different from anything that we have seen, except its close relative 18 years ago, SARS, then I don't think that the doctors have any added advantage because they are on the immunological front line. Okay, let's see. Natalie Steiner. Did I do that? Oh. Okay.
Hello, can you hear me?
Yes, I can hear you well.
First of all, thank you very much for your presentation and taking the time. Basically, my question was asked a little earlier, but trying to maybe add some remarks from you. We heard a presentation, there was one of the doctors, professor was saying that there was strong similarities on a virus CO43. Is there anything you can add on that there is similarity on CO43 and COVID-19?
So the agent that causes COVID-19, SARS coronavirus 2, is very similar to other coronaviruses that infect bats. The virus that is most similar to it that infects humans is the SARS coronavirus 1, which caused the epidemic in 2003. So other than that, it's not that similar to the regular coronaviruses that caused the common cold. Okay. Viviana. Viviana Kassam. Viviana, are you with us?
Myself. Do you hear me now?
We hear you. I hear you very well.
Okay. In one of your first slides, you were mentioning masks and whether the virus can go through a mask. So this is, I'd like to know if it does, and also how long the virus can live outside the human body, because this is something we don't know. Can clothes get contaminated? For how long? Is it true that it lives very long on metal? Should we do something, like if we go out, to not to bring the virus into the house from our clothes, or? Hello.
Okay, so excellent questions. I wish I had a very good answer. So masks, let's start with that. So the masks, the filters, the pore sizes on the masks are obviously not sufficiently small to prevent viruses from going through, but they are very efficient in preventing water droplets. So if people cough and they have a mask, water droplets from their cough or from their sneeze that might contain the viruses will not go through. So the mask might provide you some level of protection. How long does the virus live outside? And avoiding slightly the question, you know, is it alive or is it not? Unknown, simply unknown. We don't know the answer to that. I think it's fair to say that the longer it is, the less likely the virus is there to be able to be infectious. The higher the temperature, the lower the infectivity of the virus is. But we do not have a definitive answer for you, and for that I apologize. It's a question that we would all want to have a very good answer to. Okay, Pam.
I know you're not a doctor, but what are the medical experts in Israel recommending to pump up your immune system other than the obvious healthy diet and exercise?
Okay, let me just, so what are the health experts in Israel doing in order to pump up your immune system, as you ask? Well, it's actually a very good question. What we want to ensure is that our immune system is sufficiently strong, but believe it or not too strong. Sometimes, for reasons that are unclear to us, the fatalities take place because our immune system overreacts. So you don't necessarily want a hyperactive, increasingly strong immune system. So my bottom line in that answer is we don't necessarily know. Clearly, people that are immune compromised due to other diseases that they have are at far higher risk. But how to boost the immune system, I don't know. Okay, Maya, go ahead.
Can you hear me?
Yes, I hear you well, Maya.
Mia, my name is Mia.
Mia, I apologize.
Basically, you answered the first question, yes. My question was like, if you can explain how the virus survives on surfaces, plastic cartons, especially like cardboard. Today on Reuters, you know, and Bloomberg, there were very specific articles, you know, of scientists that agreed on the fact that, you know, the virus was, you know, lived on metal for 9 hours and on cardboard for 24 hours and all this. So you are saying that there are no studies, but actually it seems there are, because today in the morning, Reuters published one article on it. Are you aware about it?
Well, it could very well be that this is very, very recent. I'm not that up to speed on all the huge amount of work that's taking place. I'd be surprised if they did this with infectious viruses, because this is something that's quite dangerous. You need a Category 4 biosafety lab to study this. but I'll take your word for it. I don't really know. Okay. Adrian Weiss. Adrian, go ahead. Adrian?
Can you hear me?
I hear you well.
Yeah, thank you very much. I have 2-3 questions. First of all, lately has been reported that there are several drugs like anti-inflammatory drugs and also steroids. Okay, steroid, it's clear why may increase the virulence, but also some hypertensive drugs. So my question, if you can know something more about that. The second question, there are some reports that the incubation time it's 2 weeks, and there are some reports speaking about 5 weeks. So which is the real incubation time?
Okay.
Yeah.
Yep. 1 second. Let me, where were you? Adrian, go ahead. Okay. So there are actually several drugs on the market that are trying to be repurposed. Yes, I've heard about steroids and other anti-inflammatory agents. There are some drugs from Gilead Pharmaceuticals, drugs that hinder the replication of the virus that look somewhat promising. But again, nothing has been very definitive. People have even used chloroquine, which is an anti-malarial drug. We don't necessarily know why it works, but at the end of the day, if it does, I don't really care. So we don't know. Incubation time. Obviously, that's a frightening question, and we don't have a definitive answer. I think it's safe to say that most people have developed the disease within less than 2 weeks. But are there people out there in which it lingers longer? It could be. It clearly could be. Are they a significant proportion of the population? I don't know. I simply don't know. And once again, I apologize to that. Edward Black, please. Edward, can you hear me?
Hi, apologies, I had to unmute myself. Ed, greetings from London. Is there any argument that for people who are not in a high-risk group, not no underlying health condition, not over a certain age, that rather than seeking to avoid the virus, people should actually try to catch it and thus gain immunity by having had the disease and lived through it, so to speak?
Well, I think what you're telling us right now is precisely what took place in the UK initially, that was the one of the strategies, that the idea was that, people, below 40 years old, that the mortality is very, very low. Should they simply go out there and be exposed to that? I don't know. I think that from what I understand from the UK, they reversed their policy. And they decided to go with what the rest of the world is doing. The rest of the world is trying to reduce the number of cases regardless of the individuals. But I think what's going to take place will depend on how long this disease sustains itself. So if it's going to end quickly, as it would seem to have happened in China, then probably we're not going to differentiate between different age groups. But if it's going to linger on for a very long period of time, no economy, no society can sustain itself when everyone's staying at home. And then probably what might take place is that people that are in much lower risk, which is another way of saying young, will be allowed to leave and to increase the amount of social the opposite of social distancing, etc. So once again, I don't really know. It will all depend how this disease progresses. Okay. Robert Sarner. Let's see. Robert, are you with us?
Can you hear me, Professor?
I hear you loud and clear, yes.
First of all, thank you for an excellent presentation. So well put forward, so clear. I'm speaking to you from Toronto, which, as you may know,
yeah,
in
you guys were hit in 2003, yes. Mm-hmm.
Yes, in terms of places outside of China which suffered the SARS virus, Toronto was one of the major locations. And you've referred to SARS a number of times, saying there are certain similarities between the SARS virus and the coronavirus. So my question is, and again, I'm sure you know this, in 2002 to 2003, SARS did not have a global reach. It was limited to very few countries, in fact, in its spread. Whereas, of course, what we're seeing now with this pandemic, it's absolutely global. And what we say, almost 200 countries now are being victimized by it. So do you have an explanation why there's such a difference in the spread between these two viruses?
Yes, one reason might be that SARS, the one from 2002 to 2003, was too virulent. It's not that it was not as infectious, but the thing is, anyone that was infected immediately, or in a very short period of time, had symptoms. And because of that, immediately when someone rushes to the ER, they immediately get quarantined. So one of the reasons, quote unquote, for the success of the new virus is that it is not as virulent. And because of that, it can spread because there can be a large number of people that don't actually realize that they're contagious because they don't exhibit dramatic symptoms. And again, Toronto, we knew exactly the individual that, came on a specific plane, leaving Hong Kong, landing in Toronto, and, starting the spread of the disease in Toronto. Okay, so where are we here? Chen Avrahami. Okay, Chen, go ahead.
Hello, can you hear me?
I hear you loud and clear.
Okay, first of all, I want to thank you about your clear and interesting presentation. I want to ask, what are the most popular scientific tools that are used today to study the COVID-19? Which tools, which techniques?
What is the most common scientific tool?
Yes.
Okay, 1 second.
How it looks today in your lab?
So the tool that we use in our labs is standard molecular biology. We are expressing different parts of the virus inside bacteria. So we're not actually studying the virus as a whole. We're just taking little fragments and we're expressing them in bacteria, and we are testing their function and trying to inhibit them. People are using computational tools, so doing everything on a computer. And they're basically, the scientific community is throwing every single tool that it has in order to try to curb this virulence. Okay, so Sirio, I hope I'm not mispronouncing your name.
Yes, correct. Can you hear me?
Yes, I hear you loud and clear.
Congratulations for the webinar. My question is related to a recent study I've seen that heparan sulfate protein glycan should be present in the host cells. My question is, concerning about treatment, not vaccine, may be useful to chemically complex the HSPG in order to avoid the adhesion between the spike protein and the cells, in your opinion?
So okay. So this is it would seem that you are not part of the lay audience. This is a very technical question. So heparan sulfate is obviously part of the extracellular material, the extracellular matrix. from what I understand, the virus doesn't actually attach to that, but rather attaches to a particular protein called ACE2, angiotensin converting enzyme 2. So I don't necessarily understand why that would make a big difference, but again, it could very well be that, again, some of the recent studies that are accumulating in a rapid pace, I'm not that familiar with. Okay. Julia Menova. Julia, can you, I hear you very well, thanks.
First of all, thank you so much for the lecture, and hello from the Czech Republic. And I have, let's say, practical question.
Okay.
As, for example, again, we were talking about how virus can stay on some surfaces and so on and so forth. And for example, what about iPhones? What about smartphones? Because if we, for example, go out, we use public transport, whatever, and if we touch some surface which can have already a virus on, so do you recommend any, I don't know, disinfection of the screens, whatever? Because anyway, it's then it's somehow we use it close to the I don't know, nose, mouth, and where it can be transferred further to our body.
So I've actually heard a question such as that, and I've even seen on one of the very big web pages called CNET that people were discussing this issue. I think that, you know, any ethanol swipe will do the job probably. You know, if you're really apprehensive, you might even use stuff like Clorox. I don't necessarily know that you want to use that on your phone. But what we should try to do is to try to reduce as much as possible any contact that we have with, you know, our mouth, our nasal cavities and exterior. Other than that, I don't really have a very good suggestion because, you know, these cavities are made to ingest air. That's what they were built for. Okay, 3 last questions. Gabriela Ohana. Gabriela?
Can you hear me?
I hear you loud and clear.
Thank you very much. I have a question. I would like to know why in Italy the mortality is so much higher, and as well, I would like to know why in Italy the mortality is younger people than the other countries.
So you're asking a question that has been asked by a very large number of people without a very satisfying answer. I really don't know. It's clear that the mortality in Italy is approaching 7 to 8%, which is close to double of what it is in the world. I don't know. I simply don't know. So we need to differentiate between number of cases and mortality. I've also heard that mortality in Italy from the flu, which is a completely different disease instigated by a completely different pathological agent, is also higher, but again, we simply don't know. One second, where are we here? Okay, Martin Braun, you are our penultimate questionnaire.
Yes.
Yep. Martin, I hear you loud and clear.
Yeah, I have a question. Given that the SARS, the MERS, and the coronavirus have all been started by bats, apparently. Well, the last 2, yes, and the last one, most probably.
Yeah.
What happens, what is the risk of people who live on farms or in places outside where there are bats, and they eat some fruits that might be touched by bats? Does it propagate through the vegetables as well, or only if you eat animals who've been eating some fruits that have been eaten by bats?
Okay. So I don't have a definitive answer, but I think I can answer as follows. So if the civet could eat the fruit that the bat ingested initially and get the virus, I would imagine that we would be able to do that as well. Okay, I repeat, if there's an intermediary host that is actually getting caught by the disease because it ate something that was dropped by bats, there's no reason to assume that we would not be able to catch that as well. Let's see, and I think that is that, everyone. Okay, I guess I answered the last question as well. So I'd like to thank all of you for participating in this webinar. I hope that I have armed you with a bit more information. I apologize that I was not able to provide answers to the most important questions out there, such as when is this going to end? How long do we need, etc. But that's probably one of the reasons that you can actually realize that the authorities are continuously changing their minds, because there are no definitive answers out there. So the last thing that we should all do to one another is wish us all good health. And remember, this is not the end of humanity. This is not doomsday scenario by any even remote stretch of the imagination. So be well, everyone, and hopefully I'll get a chance to meet you in person and not digitally very, very soon. Bye-bye.